see Lawrence all over it, actually, because we've done lots of projects together before. The Origins project, which he directs at Arizona State University, plus the great debates that we did with them at Arizona State University, plus the meetings that we did called Beyond Belief. Lawrence has been a stalwart supporter of the Science Network, and I'm glad that we are having him back because he was here recently doing his book Quantum Man, the Richard Feynman biography. He will be available later on the Science Network in the series that we do called The Science Reader, and we're very pleased that Dennis Wills made this place available for us as well. Just a quick reminder that apart from his work at Arizona State University, Lawrence is, as it says here, a renowned cosmologist and Foundation Professor, Director of the Origins Project at ASU. Scientific American called him a rare scientific public intellectual. He's the author of more than 300 scientific publications, 8 books, including the physics of Star Trek, and also the source of a story. How many of you know who Miley Cyrus is? Yeah, okay. So you probably know that she in fact is in hot water at the moment because she's been doing some putting some stuff on Twitter. Let me read this for you. The singer is getting into some scalding hot water with Christians over an image she tweeted bearing quotes from a scientist. She tweeted quotes from Lawrence Krauss, which essentially proclaimed that humans are all stardust created from atoms of many stars that exploded in the universe, which is at odds with Christian teachings. It gets better or worse depending on your personal belief system, because Lawrence has also said in his charming, all-embracing fashion, forget Jesus, stars died so that you could live. This apparently has caused a stir among the Christian right wing, and it's not immediately known whether these reflect Cyrus's personal beliefs, but you could certainly look that up. I'll close I'll just bookend that with the afterword to Lawrence's book, Why There's Something Rather Than Nothing, A Universe from Nothing. The afterword was written by Richard Dawkins, and I want to read this to you, the last paragraph, because it's amazing, actually. Do the laws and constants of physics look like a finely tuned put-up job designed to bring us into existence? Do you think some agent must have caused everything to start? Read Victor Stenger if you can't see what's wrong with arguments like that. Read Stephen Weinberg, Peter Atkins, Martin Rees, Stephen Hawking. And now we can read Lawrence Krauss for what looks to me like the knockout blow. Even the last remaining trump card of the theologian, why is there something rather than nothing, shrivels up before your eyes as you read these pages. If On the Origin of Species was biology's deadliest blow to supernaturalism, we may come to see A Universe from Nothing as the equivalent from cosmology. The title means exactly what it says, and what it says is devastating. So Lawrence will now devastate us. Lawrence Krauss.
Thank you, Roger. Whoop, watch out. Okay, good. Well, I want to thank Roger for cutting short his introduction so there was time for the talk, because I always worry about that. But in any case, well, thank you all out there, and it's a little...
Turn that off.
You're going to turn that one off?
I'm going to give you this one.
You want me to give that one? Good.
Yes.
Okay, then I'm still tethered, but I can move around a little bit.
Wander.
I'll try and wander a little bit so you can see me in my head bobbing up and down. And you can't see, I'm actually going to show some slides because that's what I do. And so they're up here. But I'll try and explain them if you can't. Usually I put a quote up when Roger's introducing me because people need something to read. And so I want to give a version of a longer talk that I would have given the subject to whet your appetite. It's still going to be too long, I warn you. But in any case, there's a lot to talk about. We're going to talk about the origin of the universe, and I was hoping that Miley would show up, but I guess she's not here, is she? No. I mean, it's impressed my stepdaughter. I'll tell you that. Okay, so I want to talk about this question, which has really been around as long as people have been around, which is why is there something rather than nothing? it's really the question that everyone asks at some level, and it's been the basis of religion and philosophy for a long time. But it's not, as I'd like to emphasize, a religious or philosophical question. It is a scientific question, because something and nothing are scientific, they're physical quantities. And as a result, physics has something to say about them. Theology and philosophy have nothing to say about them. They've said a lot, but they've never said anything interesting. And instead, I want to use the real universe guide. I have a picture of the stars here. As I often say, that I used to live in Cleveland before I lived in Arizona, and every time I lectured in Cleveland, and I would have to tell people these are stars. But this is the night sky. So if one is asking the question, why is there something rather than nothing, which is what I want to get with, there's a lot of different ways to answer it. And there's is it too loud? What are we doing?
It's just more light or less light.
I don't care. I mean, it's up to the people here if they want to. Can you still see me? Yeah, I think. Are you okay with that, Roger?
More stars, less you.
Yeah, more stars, less me. That's a good idea. Okay, I am a star. But anyway, so there's a simple answer, and it's a very intellectually lazy answer. So the simplest answer is in the beginning, and then going on from there. And that, of course, doesn't explain anything about anything. It doesn't answer any questions. It just asserts something, and that's the sort of religious answer. But as I say, if we want to really be guided by the universe, because it's a physical question, so I want to go back to those stars, and the universe has changed completely our picture of everything in the last 20 or 30 years. And really, that's the reason I wrote this book, is because our picture of the universe has changed more than you could possibly imagine. And I want to introduce you to that incredibly exciting voyage of discovery. And the amazing thing is, truly amazing to me, is that voyage of discovery has led us to not only realize that it's plausible that a universe could come from nothing with no divine intervention, but we even have an idea how that might happen. And in fact, the universe not only could be plausibly created that way, but all the characteristics of the universe are those we would expect of a universe that was created from nothing. So and we'll get to that more. So let's go. So the way I want to begin is not with in the beginning. I want to begin this mystery story, which is the story of the universe, a more appropriate way. So let's begin. It was a dark and stormy night. And I'm not referring to the night the universe was created or the morning or whatever. I'm referring more to the night that Albert Einstein dotted the last period on his greatest discovery, the theory of general relativity. Its greatest work. It was the theory of gravity, but more importantly, it was the first theory that was a theory not of how objects move through space and time, but rather how space and time themselves moved. It was the first theory of space and time. And as a result, it was the first theory that could describe the universe. It was the first theory that could describe how the universe itself evolved. And Einstein knew that, but there was a problem with his theory. It didn't describe the universe in which he lived. Nowadays, that doesn't bother physicists very much, especially string theorists. But in the old days, people used to want to try and explain the universe, and Einstein was very concerned. And that's because the universe in which he lived in 1916 was a static and eternal universe. That was the conventional scientific wisdom. The universe had been around forever and would be around forever, and that was what the scientists thought. And so Einstein had this problem because general relativity suffered from the same problem that Newtonian gravity suffers from. All the high school students here know that gravity sucks. It always pulls, it never pushes. And you can't have a static universe if gravity sucks, because you put stars out there and they eventually, the gravitational attraction will pull them together. And eventually they collapse together. And here was a static universe. So Einstein was very concerned. But he realized he could modify his theory in a way that was consistent with the mathematical symmetries that had led him to develop the theory. So I want to show you how. So I have Einstein's equations here, and the people on the sidewalk can now run away. But I've actually created them in a user-friendly fashion for the, let's say, for the biologists in the audience. So here we go. The left-hand side equals the right-hand side. We're okay with that? Okay. And that sounds facetious, but it's not completely facetious, because in Einstein's equations, the left-hand side of the equations describe the geometry of the universe. The curvature, the fact that space can curve in the presence of matter, it can expand, it can contract, it can do all sorts of stuff. So the left-hand side describes the geometry, and the right-hand side describes the source of the curvature, the energy and momentum of space. So those two sides are different and important. Now, I'm a theoretical physicist, and therefore I have to write down the Greek letters, and now that's much more illuminating to many of you, I'm sure. But this was the equation that had the problem. Gravity sucks. So Einstein realized he could modify things by adding a new term to the left-hand side of the equation, that weird-looking term there, which he called the cosmological term. And that was, what he realized is such a term would produce a small repulsive force throughout all of space. So small that you wouldn't notice it here on Earth, and you wouldn't notice it where around the solar system, and all the great predictions that Newton had developed that led to Newtonian gravity and his success, they wouldn't be affected. It would be so small you couldn't perceive it. But over the scale of the galaxy, that small repulsive force could build up and hold the galaxy apart and stop it from collapsing. So he thought that would solve the problem. Now it didn't, it turned out, not least because very quickly, within a few years of writing this down, it was realized that the universe isn't static. And in fact, when I was in in Zurich recently, I got a postcard from Einstein to Hermann Weyl, who's a very famous mathematical physicist. In 1923, Einstein said, and I'll read it for you because it's in German, but also so small you can't read it. It says, if you get rid of a quasi-static universe, then out with the cosmological constant. Because he realized if the universe is expanding, you don't need this repulsive force anymore. You don't need it because if the universe is expanding, then gravity can be purely attractive. It can just work to slow the expansion. And the big question of 20th century cosmology became, is there enough gravity to stop the expansion, to stop it and make the universe collapse in a big crunch, the reverse of the Big Bang? So how will the universe end, with a bang or a whimper, became the question. And gravity could be purely attractive. So Einstein said it was his biggest blunder. He wished he'd never put it in, and etc. Now, we'll get back to that. But in 1923, people were beginning to understand the universe was not static. The person who convinced the world is this guy here. I want to show you his picture. It's my hero, one of my heroes, Edwin Hubble. Edwin Hubble is one of my heroes because he gives me great faith in humanity, and I need it, especially during this election year. Because Hubble began life as a lawyer and became an astronomer. So there's hope for absolutely everybody. And he's a great example. Hubble did many things, and one of the first things he did, which is somewhat peripheral to the rest of the stuff, but it's probably relevant to give you the context. In 1925, he used the Mount Wilson telescope to do something remarkable. In 1925, our universe consisted of one galaxy, our Milky Way galaxy. That was it, surrounded by vast eternal darkness. And there was a big debate. When you looked through telescopes at the time, you saw these fuzzy things in our galaxy, and they were called nebulae, which is Greek for fuzzy thing. And there was a big debate what they were. With the Mount Wilson telescope, Hubble was able to show that they were in fact not just fuzzy things, but other island universes, other galaxies. And we now know there are 400 billion galaxies almost in our observable universe. 400 billion. In a single human lifetime, 87 years ago, we knew of one. So our picture of the universe has changed incredibly. We're like the early map makers. And it's not too surprising that we're surprised, because we're just beginning to explore the universe on the largest scales. And it's those explorations I want to talk about. But Hubble discovered the universe was expanding, and it's so important, I think, I want to show you how. You can't see this. These are not sperm, for those that are close enough to see this. These are galaxies. And what Hubble discovered is that if you look out at galaxies that are far away from us, on average, they're moving away from us. And those that are twice as far away from us are moving twice as fast. And those are 3 times as far away from us are moving 3 times as fast, and so on. And so everything is moving away from us. Those that are farther away from us are moving faster. So what does that tell you? Well, it tells you, obviously, we're the center of the universe, right? That's the obvious answer. But it's not true. And in fact, as many of my friends remind me on a daily basis, that's not true. And what it's telling us is the universe is expanding. And so how does this tell us that? Well, the problem is we're stuck in our universe. Most of us are. None of the Republican candidates are, but most of the rest of us are. And so what we want to do is we want to get outside of our universe, but it's hard to get outside the real one. So I create one here, which not all of you see. This is probably the only most illuminating picture I'll show is for those who want to see why our universe is expanding. So let me create a two-dimensional universe, which is easy to see from the outside. I've created this two-dimensional universe, and I have these galaxies at normal intervals here, regular intervals, and a region of that, this is just a region of the universe. Then I look at it at a later time, and it's bigger. You can see it's bigger because you're outside of it. So when you're outside of it, it's easy to see the universe is expanded. But what would you see if you were in that universe? Well, very simple. Just pick a galaxy, any galaxy, say that one, and I just want to superimpose this image on top of this one, placing this galaxy on top of itself. And what would you see? You'd see exactly what Hubble saw. Every galaxy is moving away from you. Those that are twice as far away are moving twice as fast. 3 times as far away are moving 3 times as fast. And it doesn't matter what galaxy you pick. Any galaxy, you see exactly the same thing. So depending upon your mood, either every place is the center of the universe or no place is the center of the universe. It doesn't matter. Semantics. What this tells us is that the universe is expanding. And that changed everything. Because an expanding universe had a beginning. And that was profoundly important, not just for science, but in fact, for theology as well. We now understand the beginning happened 13.72 billion years ago, except in Arkansas and Ohio and a few other places. But the rest of the universe had happened 13.72 billion years ago. And it's amazing that we could say that with 4 decimal place accuracy. I would not have thought in my lifetime would be able to do that. And that, as I say, changed the playing field. And now, how did Hubble do that? He saw that distant galaxies are moving away from us. Those that are farther away from us are moving faster. Well, that means you have to measure how fast they're moving and how far away they are. So how can you do that? Well, the easy part is to measure how fast they're moving. And okay, good. I was gonna show you about that, but I realized I've been cutting things out because I didn't. This is a bookstore talk, and you're all uncomfortable, and you have to read my book to figure out how I did that. Okay. You got to encourage you to buy it, I guess. So, but he discovered by looking at galaxies and measuring objects within galaxies, both how bright they were, and therefore when they looked through a telescope, how bright they looked. It would tell them how far away they were. And by measuring the light from those objects and something called a redshift, he was able to measure how fast they were moving away, and then he discovered that. Now, having measured the fact that the universe is expanding, as I say, the big question is, how will it end? And that's the reason I got into actually cosmology as a particle physicist, because I wanted to be the first person to know how the universe would end. It seemed like a good idea at the time. And Einstein tells us to some extent, here's a picture to guide the eye. If space is curved, then it turns out it can exist in one of 3 geometries. Now, this doesn't guide the eye very well because it gives everyone the wrong impression. We live in a 3-dimensional universe that can be curved. The pictures I draw here are 2-dimensional universes because it's the only ones I can draw. So, you can picture a 2-dimensional curved universe like the surface of a sphere. It's called a closed universe. Or the surface of a saddle called an open universe. Or a flat piece of paper called a flat universe. Well, those same terms apply to our universe. And our universe is either open, closed, or flat. But you can't picture it so easily. You can sort of picture it in your mind because you can say, well, in a closed universe, if I look far enough in that direction, I'd see the back of my head. Light would go around the universe and come back. So you can, but more importantly, for a closed universe, it turns out full of matter, the universe will expand, stop, and contract again. For an open universe full of matter, it'll go on expanding forever. And a flat universe is just the boundary between the two. It'll go on expanding and slow down and never quite stop. Okay? So if we knew which universe we lived in, I thought, then we'd know what the future would be. So if we could determine what the geometry of the universe is, then we'd have the answer. And the geometry is determined by matter, so all we would have to do is weigh the universe. And so just weigh the universe and you got the answer. And it turns out we've been able to do that. It sounds daunting. And how do you do that? Well, you stand on the shoulders of giants. But I want to show you a picture of how we do it and give you a little history lesson, because I think it's amusing, at least to me, and that's all that matters. I want to take you back to a kinder, gentler time in the history of science, 1936. This is the journal Science, which is a distinguished science magazine, journal, and it was then too, published a paper in 1936 which was called Lens-like Action of a Star by the Deviation of Light in a Gravitational Field. Okay, but here's how it began, and this is important for the young people. I'm going to read you the opening sentence of this. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. Try and do that now. Try and submit an article like that now. You'll never get it published in Science, okay? It was definitely an easier time. Now, the author, of course, had some credentials. The author was Albert Einstein. But Einstein published as a result of a calculation that he thought was incredibly unimportant. The result was that he'd already shown, in fact, it was one of the triumphs of general relativity, that space is curved and light bends around massive objects. But he reasoned that if you have a very massive object and a light source behind it, the light rays can bend around on either side and come back and be focused. And the matter can act like a lens. Space can act like a lens. Or like a cut glass goblet, or this thing, if I look through it, I see many different images of the people in the room because it's got ripples. And so space could act like a lens, and that was the purpose of this paper. But he thought it was incredibly unimportant. He said it'd never be observable. And in fact, this is his calculation from his notebooks. You can see it there. But it was actually, it was so unimportant that he forgot. This is from 1936. If you look at his notebook from 1912 there, he did exactly the same calculation. He just totally forgot about it. Okay? Because he said it would never be important. And in fact, he wrote the editor afterwards, and I particularly like this, he said, "Let me thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." So that's how science is done. He thought it was irrelevant, make Mr. Mandel happy. But it's not only not irrelevant, it's the way we weigh the universe. And here's a picture of the phenomena that Einstein said would never be observable. This is a picture, for those that can see it, of a cluster of galaxies. Clusters are the largest bound objects in the universe. They contain hundreds of galaxies, or tens of millions of light years across. And anything that can fall into anything will fall into a cluster of galaxies. So if you can weigh the clusters, you can weigh the universe. And this is a Hubble Space Telescope picture, and it's beautiful because every dot in this picture is a galaxy, not a star. This cluster is 5 billion light years away. That means the light from those stars left 5 billion years ago, before our sun even formed. But it also means many of those stars no longer exist. And by the way, civilizations around those stars probably no longer exist. Each of these galaxies contains 100 billion stars, and potentially many long-lost civilizations that we'll never know about. Every time I look at a picture like this, I get inspired. But that's not the purpose of this particular picture, but it is fascinating. We can weigh this cluster because you don't have to be a rocket scientist, for those that can see it, to see there's these weird little blue things. And those blue things are multiple images of a single galaxy located 5 billion light years behind that cluster, 10 billion light years away from us, magnified by the cluster and split into several different images. And that's amazing. That tells us that space is acting like a lens. And that's fascinating. But we can work backwards. If we know general relativity and we see this image, we can ask, how much mass must there be in that cluster, and how must it be distributed to produce the image? And it's a very complicated mathematical inversion, but you can do it. And you do it, you get this picture. And this is a picture of where the mass is in the system. The spikes are where the galaxies are. But what you notice is this huge mountain of mass where the galaxies aren't. 40 times as much mass exists in this cluster as can be accounted for by all the light and all the stars and all the galaxies. And physicists, because they're so inventive, call this stuff dark matter, because it doesn't shine. And what we've discovered is not just in the clusters, but in the galaxies themselves, 90% of the mass of the universe, of the mass of stuff in the universe, 90% doesn't shine. And that's very exciting for us, because, especially particle physicists, because we know there's so much of it. We actually know how many protons and neutrons are in the universe, it turns out. And there aren't enough of them to account for all this dark matter. So that means this dark matter isn't made of the same stuff as you and I are. It's got to be made of a new type of elementary particle that we don't normally find here on Earth. That makes it exciting, because that means it's not just out there in the heavens. It's here. It's going right through your bodies as you nod off during this little talk. And that means we can do experiments here underground to look for it. And we're doing them. And one of them may soon discover the nature of dark matter. Or we could actually try and create it in the laboratory, which we're also trying to do. Where would you create it? Well, in a place that resembles the Big Bang, because this dark matter, if it exists, was created in the Big Bang. So if you can recreate the conditions of the Big Bang, you might be able to create dark matter. And where can we do that? Well, in Geneva, Switzerland, at the Large Hadron Collider, over very small scales, we create conditions that are very reminiscent of the first millionth of a second of the Big Bang. So there's a race to see if we'll create this stuff in the laboratory in CERN or discover it underground. But for our purposes, we don't need to know what it is. We just need to know how much of it there is. And we've been able to do that and weigh this system, and therefore weigh the universe and determine its geometry. And the answer is, and there's, in fact, we had a drum. We used to have bongos the last time I was here. I could ask for a bongo. There we go. Here it is. Ta-da! I hear a sigh. There you go. Well, it doesn't look very impressive, but physicists, whenever they measure something important, they give it a Greek letter to sound scholarly. And this quantity is omega, which is the ratio of the actual amount of stuff in the universe divided by the amount of stuff you'd need to make a flat universe. So if omega is bigger than 1, the universe is closed. There's more stuff than you need. If it's less than 1, it's open. If it's equal to 1, it's flat. And you can see, for those who can see this, we can weigh all the clusters, and we now find definitively that there's only 30% of the amount of stuff in the universe to make it flat. So it's unambiguous now. We know there's not enough matter in the universe to make it flat, and therefore it looks like the universe is open, case closed, end of story. Not the case, however. Because we theorists knew the answer. We always know the answer. We're not often right, but we always know the answer. And the answer is the universe is flat. We knew it was flat because a flat universe is the only mathematically beautiful universe. And these damn experimentalists were getting it wrong. Well, they always get it wrong, we thought. And it turns out, well, this is a very indirect way to measure the geometry of the universe, because you weigh the amount of stuff, you plug it into Einstein's equations, you solve some stuff, and you measure the rate at which the universe is expanding, and you see if it's what the geometry is. Wouldn't it be better to measure the geometry of the universe directly? And what's amazing is in the last decade or two, about the last 12 years, we've been able to do that. And I would never have thought it was possible. The funny thing is, actually, I would have, because I wrote a paper about it 20 years ago, but I forgot that. But we can now measure the geometry of the universe directly. And I want to tell you schematically how we do it. I won't go into the details, again, to save some time. And again, you can see pictures in the book. But how would you measure the geometry of the universe directly? Well, you have to ask the question, how would you measure the curvature of the Earth? Here, if you couldn't go around it, or you couldn't get in a satellite and see it was curved. Well, it's very simple. You draw a triangle, and then you'd ask a European high school student, what are the sum of the angles in a triangle? And they tell you it's 180 degrees. And then you say, no, but you learned your geometry from Euclid. And in a curved surface, like the surface of the Earth, it's different. Here's the equator. I could draw a straight line along the equator. I can make a 90-degree angle and go up to the North Pole. Make another 90-degree angle, come back to the equator, and I have a triangle that has 3 right angles. 3 times 90 is 270. And clearly, therefore, if you drew a big enough triangle on the surface of the Earth, you'd know it was curved. What is amazing is the same is true for a curved 3-dimensional universe. And if you could draw a big enough triangle in space and measure the angles, and they didn't add up to 180 degrees, you'd know if the universe was curved. And it turns out we've been able to find a triangle that's big enough in the last decade. From something called the cosmic microwave background radiation, the afterglow of the Big Bang. And if I had more time, I'd explain in great detail about this afterglow. It was discovered by accident in New Jersey, of all places, by 2 people who didn't know what the hell they were doing. But they won the Nobel Prize anyway, because you don't have to know what you're doing to win the Nobel Prize. No, I mean, I don't say that in a pejorative sense. I just mean if you make a big discovery, you don't have to know what you're doing. You just make it. And it was a big discovery because they discovered the afterglow of the Big Bang. Many of you could have discovered it yourself. You should be kicking yourselves. Because, well, for the older people in the audience who remember a different universe, a universe before cable TV. Because if you're as old as me, you remember that the stations used to go off the air, and then there'd be static. And it turns out 1% of the static on your TV. Here, free yourselves, unplug your cable tonight, and look at that static. 1% of that static is radiation coming from the Big Bang. It's really kind of amazing. In any case, it turns out if we look at that surface and look at a certain physical scale on that surface, which again, if I had more time, I'd describe, we can get a triangle by measuring, and the point is we have 2 lines coming from here to a ruler located at that surface. And in a curved universe, the size of that ruler will look different than it will in a flat universe because light rays can curve. So if we could measure the angular size of something whose physical size we know on that surface, we could measure the universe. And I realize that's not a comprehensive explanation that you can get, and if I had more time, I'd give it, but I certainly do in the book. But I want to show you the image. Here is a picture of the microwave background radiation taken with this system. This is a telescope, a microwave radiometer that was put in a balloon in Antarctica and went around the world, which is easy to do in Antarctica. In the South Pole, you do this. But it was a little further away. It's McMurdo. It took 2 weeks to go around, and it was called the boomerang experiment because it came back to where it started. And it measured this microwave radiation. And it looked at these lumps from the beginning of time, hot spots and cold spots. And the question is, how big are these lumps? We know their physical size. It turns out they're 100,000 light years across. We know that because of fundamental laws of physics. But how big do they look on this picture? Well, we could compare this picture, this is a different false color image, to universes we create on a computer. And here are how big the lumps should be if the universe is closed, and they should be this big, but these are bigger than these lumps. And here, if the universe is open, they should be this big as these little blue things here, but these are smaller than these lumps. But just like Goldilocks, if the universe is flat, it's just right. And we now know to an accuracy of 1% that the universe is indeed flat. So we can pat ourselves on the back. We knew the universe is flat. But there's a problem, because I just told you 5 minutes ago that there's only 30% of the amount of stuff in the universe to make it flat. 70% of the energy of the universe is missing. Where the heck could it be? Well, if it's not around galaxies or near galaxies, it must be where galaxies aren't. But what is where galaxies aren't? Nothing. Okay? So let's try and think of nothing. Well, let's just go back to Einstein a little bit. Einstein said, remember, it was his biggest blunder. He wanted to get rid of that damn term, and he was going to throw it out. But it's kind of like trying to get the toothpaste back in the tube after you've gotten it out. It's hard. And if Einstein hadn't invented this term called the cosmological term, someone else would have. Because we now think of it in a very different way. In fact, due to the miracle of modern mathematics, we can rewrite this equation. Some of you will see it here. This is a small step for a mathematician, but a giant leap for a physicist. It's not a matter of, it's easy to take this term on the left-hand side and put it in the right-hand side, but we take the cosmological term and take it from the left-hand side to the right-hand side, it has a totally new meaning. Because in physics, equations mean something, unlike in mathematics. And because they apply to the physical world. And therefore, when you put this term on the right-hand side, it now no longer looks like a piece of geometry. It looks like a new contribution to the energy of the universe. And what could give such a contribution to produce such a cosmological term? It turns out there's only one thing. Nothing. And by that I mean if you take space, you get rid of all the radiation, all the particles, everything that's in there, there's nothing left there. If that space weighs something, then it'll give this kind of term. Now, that's insane. Space shouldn't weigh anything. If you ask a 4-year-old, I was going to say if you ask the Republican candidates, but they wouldn't give an answer. But if you ask a 4-year-old, what is the energy of empty space? They're going to say nothing, because there's nothing there. And that's a good answer. But the 4-year-old hasn't taken quantum mechanics and relativity. Not in this country, anyway. So, when you put quantum mechanics and relativity together, empty space ain't so empty. In fact, it's a boiling, bubbling brew of virtual particles. And here it is in animation. This was actually shown at the Nobel Prize ceremonies a few years ago by a friend of mine who won the Nobel Prize for the theory that allowed you to predict this. This is what space looks like inside of every proton in your body. We now know that empty space is a boiling, bubbling brew of virtual particles that pop in and out of existence at a timescale so short you can't measure them. Now that sounds like philosophy because you can't measure them, it's philosophy. But it's physics because in fact, these particles, you can't measure them directly, but you can measure their effects indirectly. And in fact, this space inside of a proton, here's these particles popping in and out of existence and the fields associated with them. You may have learned that protons and neutrons are made of these particles called quarks. And protons have 3 quarks and so do neutrons. But it turns out if you add up the mass of the quarks, they only add up to 10% of the mass of the protons and neutrons. 90% of the mass of these particles comes from the energy of the virtual particles that are popping in and out of empty space. So they really do exist. And you wouldn't be here if they didn't exist. They're responsible for most of the mass in your body. So we can do it. We can say, well, look, if they're responsible for the mass of protons, let's calculate if they can give an energy of empty space. And we should do that calculation. And we end up going from this one of the most beautiful calculations in all of physics, this calculation here, to the worst prediction in all of physics. When we calculate what the energy of empty space should be, in the same way, we come up with the energy of empty space should be roughly a gazillion times the energy of everything we see, which is impossible. If that were the case, the universe would have been expanding so fast we wouldn't be here. It is literally the worst prediction in all of physics, and that's why we never talked about it. It's been around since I was a graduate student. The cosmological constant should be 120 orders of magnitude larger than the energy of everything we see. And that's crazy. But we knew the answer because we're theorists. We knew it had to be zero. Because that's the only sensible thing. The energy of empty space should be zero. And moreover, you wouldn't expect to cancel a number that's 120 orders of magnitude too large, leaving something in the 121st decimal place. It's crazy. So we knew there had to be some new symmetry of nature which would cancel things exactly. We didn't know what the symmetry was, but we knew the energy of empty space had to be zero. It was the only sensible value. But, and this is something I'll get to in a moment, it doesn't matter what we think is sensible. The universe doesn't care what we think, or what we like, or what we want, or what seems logical if you're a classical Greek philosopher. It is what it is. And so in order to find out if the energy of empty space is zero, we should measure it. And how can you do that? Well, you can measure the expansion rate of the universe. The velocity distance as a function of time. And if empty space has energy, remember it produces a cosmological term. And that is gravitationally repulsive. So if the universe is full of energy and empty space at some level, then we would expect the expansion of the universe not to be slowing down as any sensible universe should be, but in fact speeding up. And in 1998, two groups of astronomers who didn't know what the hell they were doing, but they just won the Nobel Prize, were measuring the expansion rate of the universe, and you can't quite see this, but this is the expansion rate over time, and I'm going to draw a straight line for those that can see this picture through this data set and bring the whole thing down to a horizontal level. And if the universe were sensible, these distant objects should lie on this line, meaning the universe is slowing down. But they're not. They lie above the straight line. And there's only two ways you could explain that. One, the data is wrong, and it usually is. Or two, the expansion of the universe is actually speeding up. And if you try and, just for fun, you try and fit the data and say how much energy would you have to add to empty space to make the expansion speed up, just the right amount, it's exactly what you needed. If you put 70% of the energy of a flat universe in empty space, everything fits. So that we now have a completely consistent picture of the universe, of a cockamamie universe that is stranger than we would have ever imagined. It's a universe, and the first lesson I want to give you here is that you are far more insignificant than you thought. that you could get rid of us and all the stars and everything beautiful in the night sky, and the night sky would be essentially, and the universe would be essentially the same. We are a small bit of cosmic pollution in a universe dominated by dark matter and dark energy. 70% of the universe is dark energy, almost 30% is dark matter, and we're just a little bit left over. So much for a universe made for us, first of all. But that changes everything. A universe whose dominant energy is made of nothing has changed the entire picture. And in fact, because we don't understand it at all. And that's exciting. I often say, and I was just saying to a radio host this morning, that the most exciting state to be in if you're a theoretical physicist are either wrong or confused. Because that's what you want to be, because that means there's things to learn. That's why theologians are never wrong or confused, because they never learn anything. But we have not the slightest idea why that energy is there. And if anyone comes here and lectures and tells you that, they're lying, especially if they're a string theorist. But we think its existence is probably tied to the origin of space, and, as I'll talk about in a few minutes, it will determine our future. Okay? Now, remember I told you I got in the universe to figure out the future of the universe. And the reason it's simple to figure out the future of the universe is it turns out to be similar to something we learned in high school. We teach our high school now, maybe kindergarten, we teach them this. If you take a coin, and I don't have one, but if you throw it up, it comes back down. And if you throw it faster, it goes up higher, it comes back down. If you throw it really fast, it doesn't come back down at all if there's no roof, because it's escaped the earth. And we teach high school students how to calculate that. And I'm going to show you, some of you can see this, an equation that will bring back wonderful memories from high school. We tell our students that when we throw a coin up, it has two types of energy. It has a positive piece called the kinetic energy, the energy of motion, and a negative piece we call the gravitational potential energy, which one, due to the gravity, wanting to pull it down. And it turns out it's just bookkeeping. If the positive piece beats the negative piece, then the object will escape. The total energy will be greater than zero. The object will escape. If the negative piece beats the positive piece, then the total energy is negative and the object will come back. It turns out it's exactly the same for the universe. Because if I take my little Hubble picture and I think of some small region of the universe, if the universe is the same everywhere, what happens to any one galaxy will happen to all galaxies. So we look at a galaxy a certain distance away from us and it's moving away from us with a certain speed. We know it has some positive energy, kinetic energy, but we know all the matter between us and it are pulling it back, and that gives a negative piece. And for that galaxy, if its total energy is positive, it'll escape and go to infinity. And if it does, then all other galaxies will, so the universe will expand forever. And if it's negative, it'll stop and come back. Okay? And it turns out that there's two terms. I say B is the negative piece and A is the positive piece. If B over A is bigger than 1, the energy is negative, the universe will collapse. If B over A is less than 1, the universe will expand forever. But guess what? B over A turns out to be this quantity omega. So we've measured omega is 1. Now we know the universe is flat. What does that mean? That means B is equal to A. What does that mean? The negative piece is precisely equal to the positive piece. What does that mean? The total energy of the universe is 0. The total gravitational energy of the universe is 0. If you were going to make a universe from nothing, what would your total energy be?
0.
Right. Thank you. It didn't have to be that way. It didn't have to be that way, but it is. So that's very suggestive, and I want to now, in the closing 2 or 3 hours, talk to you about what the implications are. So I want to talk to you about making a universe from nothing. And the first, and of course I have to redefine nothing. The first kind of nothing I want to talk about is the kind of nothing of the classical philosophers in the Bible. An eternal, dark, empty void, which would have been good enough for theologians until I showed them that something could come from it. That nothing, empty space, is quite simple to show something can come from it. Something will always come from that kind of empty space because nothing is unstable. Because I've already told you that empty space ain't so empty. It's full of these virtual particles popping in and out of existence. No real particles, but it's a complicated thing. Now, virtual particles are not something. So how can you create something from nothing? Well, when you add gravity to the mix, then you can create something. You see, because the virtual particles pop in and out of existence and have to go back because they take energy. And if they have energy, positive energy, they have to disappear before you can measure them. Otherwise, you're violating energy conservation. But when you add gravity to the mix, you can create particles that have positive energy due to their motion. But if they're in a strong enough gravitational field, there's negative energy, and their total energy can be 0. And in that case, you can create them with impunity. And you are guaranteed by the laws of quantum mechanics that you have empty space. It will eventually start producing particles. Just because they have 0 total energy. So the simple answer in that case as to why is there something rather than nothing is nothing is unstable. Okay? Now that should be a good enough answer, but it's not. Why? Because you can create something from it, and a lot of people don't like that. So I say that to the theologians. They say, well, that's not nothing. That's something because there's space there. Where did the space come from? So then I say, well, that's what I just said. So then I said, well, space itself can come from nothing. Because if you apply quantum mechanics to gravity, and we don't have a theory of quantum gravity yet, but we know if you did, since gravity is a theory of space, space itself becomes a quantum mechanical variable. And, if we apply quantum mechanics to stuff in space, we can get virtual particles popping in and out of existence. If you apply quantum mechanics to space, then space itself can pop in and out of existence. And where there is nothing, you can create universes from nothing. Space from nothing. And those spaces will go into existence and then go out of existence. You'll create virtual spaces. Now, the only kind of spaces that can live forever, those are those that have zero total energy, just like the particles. And you say, oh, great, well, we live in a flat universe that has zero total energy. But I'd love to say that, but that's not true. And I want to actually be honest. It turns out we can't say for sure that the total energy of a flat universe is zero. I showed you that the gravitational energy is zero, but particles have rest mass, E equals mc squared, and therefore we have never been able to do the calculation to see if a flat universe has zero total energy. There's one universe that we've been able to calculate that show it has zero total energy, and that's a closed universe. But we don't live in a closed universe, we live in a flat universe. So what gives? Well, the point is, if you create closed universes in and out of nothingness, those closed universes will be very, very small, microscopic in size. And on average, in fact, almost always, they'll collapse in a time scale of a millionth 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 of a second. As is obvious from the length of this lecture, our universe has been around longer than that. But how can you make a closed universe that will survive long? Well, before it collapses, if you fill the empty space with energy and cause it to start expanding very fast, you can take an initially small universe and blow it up. Now, it turns out from particle physics, all of our ideas suggest that the very earliest moments of the Big Bang, that's exactly what happened. It's a theory called inflation. It was invented by particle physicists because it solved some problems in particle physics. And it will blow the universe up by a factor of 10 to the 90th in a fraction of a second. But what happens then? Well, like a balloon, if you blow up a balloon, the surface of the balloon gets flatter and flatter and flatter. And therefore, after inflation, what will the universe look like after inflation? It will look like a flat universe. And therefore, if you were going to create a universe from nothing, you'd create closed universes, but the only universe that could survive long enough for anyone to evolve in it, and I can still say that word in the United States, evolve in it, is a universe that expanded very greatly at early times, and therefore the only closed universe that can live long enough for us to be in it, to ask the question, why is there something rather than nothing, is a universe that looks flat. So if the universe came from nothing, it must look flat. But if it looks flat, it could have come from nothing. Now that should satisfy everyone, but of course it doesn't, because that's a universe without God. So people say, well, that's not nothing. Because you might not have particles, you might not have space, but you got the laws of physics. Who created the laws? And the last kind of nothing I want to, well, this is just words that I just said to you because I don't want to. Okay, here we go. The last kind of nothing is the kind of nothing where I want to point out that even the laws themselves may be accidental. They may have arisen when the universe arose. The laws of physics, in fact, we have every bit of evidence to think that the laws of physics may just be an accident. It's sad, but true. And let me tell you why, and I think it's probably the last thing I'm going to talk about. Yeah, okay. This is a picture some of you can see. It's a brief history of time. It's the density of all stuff, matter in the universe. It falls down. The energy density of empty space remains constant, and those two curves cross at one point. That's today. They're within a factor of 3 of each other today. But if that's true, we live in the only time in the history of the universe when the energy of empty space is close to the energy of matter. And Copernicus told us it's not supposed to be the case. Why should we be living 13.7 billion years after the Big Bang, this random time, the only time in the history of the universe when those two numbers are the same? That's crazy. And so some physicists have come up with an answer. They say, well, maybe the answer is that galaxies exist. Now, why should that be the case? Well, if I made the energy of empty space, say, 50 times bigger for those that can see this graph, these two curves would cross not today, but at a much earlier time. When would that be? That would be the time when galaxies first formed. But if the energy of empty space is bigger than the energy of matter before galaxies formed, the energy of empty space is gravitationally repulsive. So matter would fly apart before it collapsed to form galaxies. So if the energy of empty space were too large, no galaxies would form. And some people have suggested that maybe that's telling us something, and it's led to something I call anthropic mania. Because it says if there's many different universes, and in each universe the energy of empty space varies randomly, only in those universes in which it's not much greater than we measure today will galaxies form. And only then will stars form, and only then will planets form, and only then will astronomers form. So the universe is the way it is because it's measured. It sounds ridiculous, doesn't it? So we're laughing. But it's not. It sounds like almost like a tautology. To some people it sounds religious, by the way, because it sounds like our universe is fine-tuned for us. But in fact, it's much more like natural selection. I mean, bees can see the colors of flowers so they can get nectar, not because they were designed to do it, because if they couldn't do it, they wouldn't reproduce, they wouldn't survive. It's not too surprising to find ourselves living in a universe in which we can live. I mean, it would be quite surprising to find the opposite, in fact. So really, this is kind of cosmic natural selection. It's still depressing to me, because it means that one of these fundamental quantities in nature is an accident. It's not something we can predict. It also suggests that maybe there are many different universes, and ours is just one that happens to allow galaxies to form. But you see, particle physicists have jumped on this idea, because particle physics is way ahead of cosmology. In cosmology, there's one fundamental number didn't understand, the cosmological constant. In particle physics, there's many more numbers we haven't understood for much longer. So we're way ahead. Why is gravity the weakest force in nature? Why is the proton 2,000 times heavier than the electron? Why are there three forces? Or not three forces, four forces, but why are there three generations of elementary particles? All these things are things we want to explain, or we used to want to explain. But now particle physicists are saying, this is great. Maybe we don't have to explain anything. Maybe it's all an accident. And if any of those numbers were changed, we wouldn't be here. So in that case, you don't need a theory of everything. You just need a theory of anything. We have such a theory. It's called string theory. And for those who can see this cartoon, this is my one cartoon summary of string theory. One guy says to another, I just had an awesome idea. Suppose that all matter and energy is made of tiny vibrating strings. And the second guy says, okay, what would that imply? First guy says, I don't know. So that's the history of string theory for the last 40 years. And it used to be a theory of everything, but one of the big depressing things about string theory is that it predicts an 11-dimensional or 10-dimensional universe, and we only see 4 dimensions. So you got to get rid of those extra dimensions by curling them up in small scales. But it was soon realized that every different way you curl up these extra dimensions into small scales produces a different universe in 4 dimensions. So string theory doesn't predict a unique 4-dimensional universe. It predicts maybe 10 to the 500 4-dimensional universes, in each of which the laws of physics are different. Well, that's exactly, in some sense, what we're looking for, that landscape. And if it's true, this multiverse means that, in fact, every different time a universe is created and curls up, different laws of physics result. And if that's the case, the laws of physics we measure literally come into existence when the universe comes into existence. And the last bastion of hope that you need something or someone to create a universe intelligently goes away. And so I want to conclude with a few statements. First of all, the multiverse, which is in this case the possible existence of many different universes, in this case plays the role of the prime mover of Aristotle, or the first cause of the Catholic Church, or whatever term you want to use. Because people like to think that if things were a beginning, if there's a beginning, there must have been a cause. Now, that's not always true, by the way. But in this case, so the idea is they invent a God that's eternal and lives outside of our universe. Because it's lazy thinking. It's in a way to get around that incredibly difficult issue. But if we have a multiverse, that multiverse can have been eternal. And in that multiverse, our universe could have been created 13.72 billion years ago with the laws of physics coming into existence as it was created. Or it's equally possible, and this is perhaps even more plausible, that before doesn't mean anything. Because you'd have a cause, you need a before. But if space and time are determined by matter, which is what general relativity tells us, when our entire universe was created as a quantum object, it's quite likely that not only did space come into existence, but time came into existence. And if time came into existence, there's no before. So the question is moot. So, and I want to point out that we've been driven to this idea not philosophically, and when I've debated some apologists, they say, oh, well, you just created the multiverse because you didn't like God. Well, it's true I don't like God. But the point of this is that we've been driven to this idea not because of our philosophical prejudices, but because of nature. Because nature has driven us there. And that seems to me profoundly important. And, well, the last thing I want to do in deference, I guess, to Christopher Hitchens, who I know has lectured in this very store, right? And he was a good friend of mine, and there's no one quite like him. And we all mourn his passing. And Christopher was actually writing the foreword for Richard was writing the afterword and wrote it, but Christopher was writing the foreword for this book when he got too ill and had to stop, and it was a great loss for me as to the world. But Christopher, when I told him about all this stuff, and I used to talk about science because he was fascinated by it, and I told him what was going to happen in the future, he said, you know what? Nothing is heading towards us as fast as it can be. Because if space is dominated by the energy of empty space, if that's the dominant stuff in the universe, the expansion of the universe is speeding up. And that means all the galaxies we now see are moving away from us faster and faster. And if we wait long enough, about 100 billion years or so, all the galaxies outside of our local cluster will be moving away from us faster than the speed of light. It's actually allowed in general relativity. And that means they'll disappear. And in the far future, not our future, but in the far future, around some star, in what will be left of our Milky Way galaxy, there'll be astronomers who will evolve on a planet and discover the laws of physics and electricity and magnetism and quantum mechanics, and they'll build telescopes and they'll look out, and what will they see and what will they think? They will think they lived in the universe we thought we lived in 100 years ago. Because all they'll see is one galaxy, surrounded by an eternal, dark, static, empty void. They'll get the wrong picture, and it'll be the picture we thought we had 100 years ago. I find that kind of poetic. All the rest of the information will have disappeared. And eventually, of course, the stars in our own galaxy will disappear. And then what will we have? Nothing. And that's what Christopher was saying. Nothing is heading towards us as fast as possible. And in fact, then the simple answer to the question, why is there something rather than nothing, is quite simply, just wait, there won't be for long. And it's, of course, humorous, but it's also significant, because it's the conceit we have as human beings. When we think of evolution, we think that we are the pinnacle of evolution, that it stops here. Well, of course, it doesn't stop here. Lots of things are still evolving on the planet, and so are we humans. We also feel that the universe was created for us, and it stops here. It's always going to be like this. In the future, it won't be anything like this. And in fact, there'll be nothing. We'll return to a state of nothing. So, to conclude, science has demonstrated that it's plausible that the universe was created from nothing. And not only that, but every characteristic of our universe that we can measure is consistent with a universe that came from nothing. It's highly suggestive. That doesn't prove the universe came from nothing. But to me, the fact that it's even plausible is remarkable. The fact that science has come to that threshold. And while Roger read Richard's very kind quote comparing my book to The Origin of the Species at the end of the book, I won't do that, but I will say that at least there's some philosophical connection. Because before Darwin, life was a miracle. There was no physical mechanism to understand the diversity of life on Earth. And he showed by mutation and natural selection, you could, in principle, make it plausible. He didn't know about DNA. He didn't know about the details of genetics. It was plausible. And what we now are with cosmology have gotten to the point where we've been able to see that it's plausible to make a universe from nothing without God. And God is therefore at best redundant. And I personally find that very satisfying. Now, the other thing I want to point out is that this question, something and nothing, don't have the meaning they had before. Something and nothing, the meaning is completely changed, and it's changed because physics has changed the meaning of something and nothing. And so it's not the same question as the classical philosophers and theologians asked. So when I'm yelled at by saying, you're not talking about the nothing of classical philosophers, I say, who cares? Because that's not relevant anymore. Science has changed the definition of something and nothing, and I care about the nothing of reality, not the nothing of ancient Greek philosophers or theologians. And the interesting question is rather not why is there something rather than nothing, but the really interesting questions are, how did the universe evolve? And how can we find out? Those are the questions that matter, and those are the questions that science is addressing. So, you know, I've told you two things. I've told you a lot. But the lessons I want you to take away are the following. The first I already told you. You are more insignificant than you ever imagined. The last lesson I want to give you, which is at the end of the talk, is the future is miserable. So you're insignificant and the future is miserable. Those are the two things that you should realize. And you shouldn't be depressed. You should be excited. Because here we are, living at this random time where we're lucky enough to have evolved a consciousness where we can appreciate the universe. And instead of being depressed by a purposeless universe that's going to be miserable in the future that doesn't depend on us, we should be thrilled. We should enjoy our brief moment in the sun. And for those that isn't enough for, if you think about the future, the far future, about those beings, you'd say, well, we're going to be lonely and ignorant, but we'll be dominant. And all of us who live in the United States are used to that. Thank you very much. You want to use this one? Okay.
Where is it?
It's,
there we go.
Okay. Turn your mic on.
Can you hear me?
Yes,
Good.
your mic is on, Roger.
So, Lawrence, great talk. So we are more insignificant than we thought. You are more insignificant than you thought.
Well, you are, Roger.
And the future.
You are.
The future is miserable. Actually, somebody sitting next to me said that's what my wife said to me last night. So. You mentioned hitch. What we're going to do now is I'd like to actually make an opportunity for some of you to ask questions. We're not terribly well equipped to be rushing around with microphones. But
I'll repeat them and
we'll figure
pick a
something
few.
out. Maybe even I can even get to some of you. Let me play, use my prerogative and play
What a
baffled
surprise. Okay.
devil's advocate, which is a role I can do very
Yeah.
well. To begin with, and ask you the kind of questions I get when we do Beyond Belief and things
Yes.
like this. You mentioned Hitchens, and on the last page of the book you say Hitchens said nirvana is nothingness.
Yes.
And you then go on to say a more extreme version of this eventual retreat into nothingness may be inevitable. Eventually, universe must decay to a state in which the energy associated with space will be negative, the universe will then recollapse inward to a point, returning to the quantum haze from which our own existence may have begun. So the question then becomes, why is there nothing? Because there'll be nothing then, right? So there'll be nobody to ask this question about why is there nothing rather than something.
Well, in fact, you hit the key point. The simplest answer to the question, why is there something rather than nothing, is if there weren't, you wouldn't be here to ask the question. It's that simple. Because most of the time and most of the space may be nothing. And the only places where you can ask the question, why is there something, is where there's something. So it's not too surprising. I don't see the big point. I don't see the big problem.
Okay, so here's the other kind of thing I get.
I don't know, maybe I should turn this off.
People say things like you talk about multiverses, you talk about the Large Hadron Collider, maybe they found a Higgs boson.
Yeah.
You talk about the Big Bang and having quantified that down to a fairly well, but they still want to know what came before the Big Bang. If it's expanding, what?
Well, there are two answers. I tried to give them both. One is, It's not a good question. Because there may be no before. Before is a concept that depends on time, and time may not have existed until the universe came into existence. So there was no before the Big Bang. It's just not a good question. Which is really okay, because science usually changes the playing field. And things often seem confusing to us, and what science does is make it less confusing ultimately, because it changes the meaning of things. It changes our understanding of things. So that's one possibility. But the other answer could be that there is an eternal multiverse. And in that multiverse, there are universes being created all the time. Ours was one that happened to have been created 13.72 billion years ago and expands forever, maybe. Other universes may be being created today and may be colliding and maybe contracting and going out of existence. In that multiverse, if you wish, it's kind of like Fred Hoyle's steady state universe. In that multiverse, it could look at any time always the same. There are always universes being created, always universes being destroyed, and ours just happens to be one, and we seem special because we live in it. And that's a characteristic that's an unfortunate human foible. We tend to think things are significant because they happen to us. I talked about that when I talked about Feynman here almost a year ago. You know, Feynman used to love to go around to people and say, "You won't believe what happened to me today. You won't believe what happened." They'd say, "What?" He'd say, "Absolutely nothing." Because most of the time things happen to us and we think they're significant. We can have stupid dreams for hundreds of dreams, thousands of dreams, and then one day we dream that a friend is going to break their leg and their friend breaks their arm, and we say, clairvoyant. Most of the time things are not significant, and we ascribe significance to them because they happen to us. And we seem to ascribe significance to this universe because it happened to us. But that doesn't mean it's significant. It's only significant to us.
So let me just, could you give me a show of hands? How many of you actually are comfortable with this view of the universe? Or
Well, there's a few.
Well, there's a few.
But let me say that, you know, that's the great thing. I said it earlier. The universe doesn't give a damn if you're comfortable with it. And just get over it. Okay.
All right. So are there anybody has some questions? Any of you have some questions?
Lots of them. Okay, we'll take a few outside for the people. Is that all right for the people who are freezing? Can you scream, and I'll repeat it.
Okay, so I have all these friends that show me books, and some of them are these books that say, oh, you know, you cosmologists are all wrong. It's really the electric universe, and, you know, the redshifts are really just Compton scattering, and so on and so forth. I never know what to say to these people. What would you, a cosmologist, say to debunk these theories?
Well, first you tell them they're wrong.
Okay.
And well, the question is, so he has friends who don't believe the Big Bang because they think all the stuff we see can be explained by other stuff. The answer is it can't. And in my book, I talk about a little wallet card I carry around. And for those people, I show them to say, see, there's a Big Bang. It happens to be the abundance of light elements, which we predict correctly in the Big Bang to 10 orders of magnitude. And there's no other way of explaining that. But it turns out every bit of data, not just one, but everything we've measured about the universe is not only consistent with the Big Bang, but only a Big Bang. In fact, you might explain one bit of data and say, the redshift is due to something else. But then, why do you get a universe that's 13.72 billion years old when, in fact, the redshift tells you the universe is 13.72 billion years old, but you measure it independently, you get the same answer. If it walks like a duck and quacks like a duck, it's probably a duck. Now, it could be that God created it just to look that way. And I've often thought that, I completely disagree with Einstein. If there was a God, he'd be malicious but not subtle. And so the only time I ever believe in a God is when something bad happens to me, by the way. But in this case, unless you believe there's an amazing conspiracy it's just like, it would be the same as a conspiracy that says, look, this universe is 15 seconds old. Now, I can't prove it isn't. I can't prove we weren't created all here 15 seconds ago with the image of a universe and memories that happened of the intolerable, uncomfortable time you've just had the last hour. I can't disprove that, but if you want to move forward, accept what you see, and in fact, what we see is consistent with only that. Every bit of data is consistent. Take one more out there. It'll take two more in here, and then I think we'll let people. You can ask me questions afterwards.
See how many people actually do believe in some concept of a creator.
Oh yeah, I don't really care, but how many people believe in a creator? I've been told. A few. How many people believe in a creator? Well, there's a minority in this. I only see two people. Three. And it's fine. And the point again, it's not a vote. It's not. I didn't say there wasn't, and I should make that point. I don't declare myself as an atheist as a rule. I've been influenced by my friend Christopher Hitchens, and I'm an anti-theist. And that means I can't say with certainty that there's no creator or no God. What I can say is I wouldn't want to live in a universe with one. I wouldn't want to live in a universe with some cosmic Saddam Hussein pulling all the strings who doesn't put you in jail for a few years for doing something wrong and torture you, but tortures you for an eternity. That I don't, not the kind of universe I want to live in. Yeah?
I'm finding it very challenging to wrap my mind around the concept of nothingness altogether.
Me too.
I don't have much physics background, but if everything is happening at once, isn't that pretty much what people think now in physics, that there is no time?
Well, no, it's not. Okay, so the question is that you're having a hard time wrapping yourself around nothingness and everything happening at once. And it's not quite that way. It's not as crazy as that. If you watch What the Bleep Do You Know or other nonsense, you'll hear that. But quantum mechanics is really crazy. And it says that at a subatomic level, indeed, elementary particles are doing many different things at the same time. Electrons, which act like they're spinning, are spinning not just in one direction, but all directions at the same time. We measure them, we find out they were spinning in one direction. But before we measured them, they were spinning in all directions at the same time, and we can show that that's the case. So it really is crazy, but it tells us that in some sense, on the smallest scales, anything that can happen is happening, and all possibilities are being explored at the same time. So that's true at a microscopic level. And it is crazy, but it is one of the reasons there are virtual particles, because they can come in and out of existence because it's possible. And as long as they go out of existence in a time so short that you don't measure any violation of the conservation of energy, quantum mechanics says it's possible. And it happens.
Is this
Look.
idea of nothingness something that any human can grasp? Because I sure as hell can't.
Well, but no, in the sense of a word, it's hard to understand nothingness because it defies our classical pictures of sensibility. But quantum mechanics defies our classical. A sensible universe is nice, but it's not the one we live in. And I've argued that. I debated this huckster called William Lane Craig in North Carolina as a Christian apologist a year or two ago. And he said, this isn't logical. And I said, the universe isn't logical. It doesn't define classical logic. In fact, he said it's like saying 2 + 2 = 5. So I stripped, which I love to do. And I happen to have a T-shirt under my coat and tie and jacket, shirt. And it's a T-shirt that my wonderful partner gave me. And it says, 2 + 2 = 5 in the limit of extremely large values of 2. And the point is, when you have large numbers, classical logic goes out the window. And then the universe doesn't obey classical logic. And the fact that we as humans can't conceive it just means we're limited. We can't conceive of a curved three-dimensional space. I can write it down mathematically, but can I picture it? No. We're limited. But what's amazing is that in spite of our limitations, that our intuitive understanding isn't sufficient to grasp it, we nevertheless have been able to be dragged kicking and screaming slowly by the universe itself to realize the way it really is, even if it's stranger than we could have ever imagined. And in fact, that's the real moral is that the universe is stranger than we could have ever imagined. Every time we open up a new window on the universe, we're surprised, which is why we have to keep looking. If we just did this all in a closed room, we would never come up with a universe that's as interesting as the one we actually live in. And that's why physics is interesting and philosophy isn't.
So, those of you who, by the way, weren't able to see the illustrations and so on that Lawrence has been showing, when we get this up on the web, on the Science Network, you'll be able to see them.
Or better still, you could look for them in the book and buy the book.
Whichever, provided, what's the time scale here? Do we actually have time?